Okay, I'm going to make some Python code today to deal with really three different situations with latitude, longitude, and distance and direction. Now, you can see right here, this guy named Thaddeus Vincenty from Poland moved to the United States, worked for the U.S. Air Force for 20 years, and then joined the U.S. Geological Survey, came up with something spectacular. The Earth is not perfectly spherical, so computing distance is a little complicated. But Mr. Vincenty invented this procedure back in the 70s, if you can imagine doing this without computers. He came up with these formulae that we've been using ever since. Very impressive what he came up with. So he came up with two situations. If you have 2 points, latitude, longitude, converting that into distance and direction, that's his inverse problem. Spectacular, really neat how it does this. There is a looping function in here that as you approach the correct answer, it'll get closer and closer as you go through this, and I'll show you that as I build my Python code. The other problem he came up with was the direct problem. You have latitude, longitude, and you do a direction and distance from that latitude, longitude, and it will end up at an end point somewhere. Similar situation, you run through the information, and then it will eventually go through a loop to find out what that ending latitude, longitude is. He did, a year after he published in 1975, change his A and his B, this A and this B. So initially he used this sequence, but afterwards he said this would be better. And so this K1 to build the A and the B, and that's what I use now. It didn't really make any difference. I was still getting the same answers with this A and B as with this A and B, but if he thought it was important, I think it's important. So let's, and then there's one more problem that I'm going to build in my Python also. So first, we're going to do the indirect, which is as I make these functions, the first one, the indirect, I'm going to take latitude in degrees, longitude in degrees, and a latitude in degrees and a longitude in degrees, so 2 points, and we want to figure out what is the distance between them. So starting with this, we take A, which is the radius at the equator, that's in meters, and then our Earth is a little bit squattier than it is tall. If your radius at your equator is 300, the radius to the pole is 298. So it's a little bit shorter to the poles than it is to the equator. So we have these. A is the equator radius. F is how the flattening that we get from the Earth, because it's a little squattier than it is wide. And then B is the polar radius. I'm going to take all of those latitude, longitudes and turn them into radians. I start out with degrees, and I get to turn them into radians. So I'll have my latitude and longitude for both points in radians, and then we start going through the formulas that that Mr. Vincenty came up with. So let's see if I can get these both on the screen at the same time. So first, the inverse problem. We start up here at the top. So you have your A, your F, and your B. I had to turn them into radians. He already had them in radians. So you got your latitude of both points. We come up with the U, the arctangent, 1 minus F times the tangent of the latitude of the first point in radians. And then U2, same as here. And then this point here, L, is our beginning L. It's going to convert. We're going to use lambda. And the lambda is going to evolve as we start doing this loop. So we come down here and we have our sine, giant square root of all that gibberish there. And then the cosine. And then our sigma. And then our sine of alpha. Our cosine squared alpha. And then I did the cosine of 2 sigma m. That's this. Now there was 2 versions I could have used. I used the first one. Not that one. I used the first one. Then we get the C. And then our first iteration of lambda. So we had this lambda, then we went through all of this and we got this new lambda. And then we keep doing this cycle till this lambda settles in on a number, so where it's not really changing anymore. And as I tried out lots of things, you could probably get away with 4 times, but I went 7 just to make sure. And then once it gets to there, we come out with all of these numbers. They've been adjusted as we've cycled through. Then we get little u squared. Big A, this big A is this, but it also works if you use his new formula of this. Big A or this big A, either way they work out the same. And big B, and then we have the change of sigma, the 2 sigma m, the 2 sigma m is those 2 things added together. Our initial sigma, let's see, where are we? The initial sigma there. Change of sigma is all of this business there. So running through all of that. And then we end up with S, or I called it the distance. So we run that through and it pops out distance. Now also we get from these guys the direction of the from point 1 to point 2, and then the backwards direction. That's what I get from these. I get the direction from point 1 to point 2 in radians, and then I convert it back into degrees. And then the back azimuth in radians, and then I convert that to degrees. And then I also did an impact azimuth, but I use that for personal reasons. So I'm going to kick out the distance, the launch azimuth, the back azimuth, and then the impact azimuth. So as we run those things, let's run down here. Where did I have one? Bipolar. I guess I don't have one. So if I had to do something like this, Let's do, I'm going to run this code just to store the functions. And then I'm going to want, let's let that finish. I'm going to pause for a second. So LL distance needs 4 items, latitude, longitude, latitude, longitude. So let's do something like 30 degrees latitude and 120 degrees longitude. I want to find the distance to negative 10 degrees latitude to 150 degrees longitude. And it kick out 4 items. Ooh, pi is not defined. Hold on. I need this. I need all the functions from sine, cosine, and such. So let me import all of those functions in. Square root, pi, cosine, sine, tangent, arctangent 2, and arcsine. Looks like I'm not using arcsine, but that's okay. Anybody underlined? Okay. So run this again. That's all stored in there. So now, when I'm going from here to here, it's going to pop out the distance in meters, the direction in degrees from point 1 to point 2, from point 2 to point 1, and then the impact azimuth as I come into point 2. So there's my distance in meters. 5,469,399 meters. Here's the direction of launch. Here's the direction back. And then as I'm coming into point 2, that's the direction I'm coming in at. So that's my lat long distance. Okay? Now we want to do, his other problem was, what if I have a point? I have a direction, and I have a distance from that point. This is his direct problem here. So I'm going to start out similar. There's my A, my F, and my B. I'm going to turn my direct latitude and longitude into radians. I'm going to take my direction that I'm leaving point 1 at, turn that into radians. Go find U1, sigma 1, sigma alpha, U2. I did the first part, not the second part. Wait. Yeah, I did the cosine one. The cosine. Oh, that's this one. U2. I did the second one. U2, 1 minus sine squared, alpha squared, beta squared minus 1. Did the A and the B. Here I used his 1976 version. A and B, and then we come out with a sigma. That's here. The distance, B and A. Let's see, where's direction? Big B, big E, sigma. That's sigma right there. And then I'm going to loop through this guy I was going to do 7 again, but it stops messing around after about 2 or 3. I did 4 just to be sure. So I did TSM, that's this one, 2 of these. I had to use a T because Python won't let me start a variable with a number. And then 2 sigma 1 plus sigma. The difference of the sigma is that giant formula here. And then I got a new sigma. So I started out with this sigma, but as I cycle through, I get new sigmas. And it settles down on a sigma. Then I can go start getting my latitude of my second point. That's this thing. Got my lambda, a C, an L, and then I can get the longitude of my second point. Turn those things into degrees, and I'm going to kick, and then I have an impact azimuth coming in at the end. I used my previous function to get that, and then it kicks out the final point and the launch azimuth, which we started with, and then the impact azimuth. So let's try something like that. Let's say, and I called this one V polar for Vincenty, V polar. I need a beginning latitude and longitude. I need a launch azimuth and a distance. So let's say we're heading, let's head 100 degrees, and let's go a distance of 1,000,000 meters. And let's see where we end up. So that's going to be our ending latitude, longitude. That's our beginning launch azimuth, and we come in at that azimuth at the end. Now, those are Vincenty's 2 sets of formula. Hasn't changed since the 70s. Everybody still uses it. This is the standard of how we compute distance on our planet. But I needed one more thing. What if I had a far point, and I knew the direction and distance to it, but I want to know where I am? So I used Vincenty's formula backwards. So I called it reverse Vincenty polar. I start out with a far latitude and longitude, the direction to it, and the distance to it. And I want to come out with where am I? So the way I did that is I cycled backwards. So I took an initial back azimuth and then cycled through and looked at the difference of what it was supposed to be and cycles until it gets closer and closer. And then I can pop out with, I must be at this latitude, longitude, and this is the direction that I started with, and this is the impact azimuth. So it's backwards of what Mr. Vincenty does. So if I started out with these points, and I want to kick out here, what happens? So reverse polar. So let's see. I do this. So this is where I started, and this is the direction of the 2 things. And let's see. And that's my distance. So let's run this and see if we get the same answer going the other way. So we start out at negative 60.4640279, blah, 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 blah. Close enough. And negative 67.6014287, blah, 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 blah. And I need to know the launch azimuth. So that was the 45 degrees. and the distance of 5006250, and we get that same numbers. Okay, well that is that. Mr. Vincenty came up with some brilliant things, and now I've made some functions that I can use to compute distance on our planet.